finally gonna start examples after all that.
After all of this, finally starting examples.
After all, yeah, all the.
Hopefully, I remember all
All
of
right,
that.
so this right here, what I laid out right here is the method to solve problems involving energy. So to solve problems, to solve usually is which is motion problems. To solve motion problems involving energy, we apply the law of conservation of energy, which is energy can't be destroyed or created. It can only be transformed from one system to another, or transferred from one form to another, and that the total energy must remain constant. So that's what it states. And the equation, this is the equation form of that. So if an object travels from point A to point B, so either potentially, kinetically, so it depends. So kinetic energy of the object at point A plus potential energy of the object at point A plus work done by all non-conservative forces from point A to point B equals to the kinetic energy at point B and PE at point B. Or you could just see it as this: kinetic energy sub A plus potential energy sub A.
What's
Remember this?
What's the equation you could get everything from this?
Yep. This is your one equation. This is your one equation.
Oh yeah, yeah. Remember he said remember you guys just I think it's like 2 chapters, right?
Yeah.
2 chapters of the word notes.
Yeah. So the method that the way you would take start solving these is you draw the problem out like always, like any other problem. You always label your zero reference PE level, which is labeled at the lowest point. Again, it's arbitrary, so it doesn't matter where you label it. And label point A at the starting point of the object and label point B at the ending point. And then you just apply the equation and solve. So this right here is your method to solve each and every energy problem so far.
Okay.
Yeah. All right, let's take an example.
Right.
2 examples.
All right. Only 2?
So, yeah.
It's gonna be hard ones, I bet. There's always the 2 hardest ones.
2 hardest ones. Yeah, one of them is gonna be simple. All right, we'll start easy. So, student, these examples that I got right here are straight from the professor.
Yeah, I know. Yeah.
Yeah. So a student.
He's definitely gonna give one of these.
Yeah, probably not this one. This one is, but maybe he might give this one, but for a multiple
choice. Yeah.
Yeah. So a student throws a 10-kilogram ball.
That's like 20 pounds.
Around. Ball up into. So a student throws a 10-kilogram ball up into the air with an initial velocity with an VI equals to 60 meters per second. And all it's asking you is how far or how high, actually.
We do have to draw the free body, right?
Yep, always. How high did the ball go? So how high did the ball?
The highest point, right? Or
yeah.
Wait, there's no energy.
We're looking for the highest point.
Is there energy involved in this?
Yeah, there is.
Holy cow.
This would be, yeah. So a student throws a 10-kilogram ball up into the air. So we could draw that out.
But it doesn't say, the question doesn't say anything about energy, though.
Nah.
How would you know it's energy?
Well, it's going to ask you how hard you're going to have to think. A student throws a ball, so he threw a ball.
Yeah.
Meaning you have some type of potential energy and also kinetic energy. They gave you a velocity. And they're asking you how high did the ball go. They're looking for an H. And you know that potential energy has an H.
Yes.
Okay.
MGH. So I'm
going to draw the problem out. Yep, MGH. So this is ball.
Yeah.
And he throws it up into the air.
Okay.
So let me drag this guy.
It's going to hit him, man.
So here it's point A. Remember, we always label point A.
Point B.
Point
And then
B.
a 0 P
And
is
here,
A. I mean, yeah.
yep, you just draw your 0 PE level like this.
Ooh.
At the lowest point, like that. This is your 0. You see how we chose it to the lowest point? We didn't choose it here.
Mm-hmm.
We chose it there. That's
Yeah.
the lowest point of the object.
Yes.
So that's why.
Oh yeah, that is the lowest point of the object, and then it went up.
Yeah. Yep. So this right here is 0 PE level.
Mm.
And like always, you just write out your equation.
Oh, if it asks
energy.
what if it asks like how long it takes for a ball to drop, like the
time.
Yeah, like let's say a student throws a 10-kilogram ball up in the air with a initial velocity of 60 meters per second, right?
Yeah.
How high did it take for the ball to go up and come down on the ground? Then the 0 P would be underground, right?
Yeah, you would make it, and then that would be a kinematic question because you're solving for time.
Oh, you
and
are.
energy doesn't have time.
Oh yeah.
So you'd probably be solving. You probably.
Oh, that is the time. Yeah. This is how high.
Yeah. We're not looking for a time. We just want to look for the height.
Yeah.
So like always, you just write out your energy equation. So just kinetic energy at A plus potential energy at A.
Mm-hmm. Oh yeah.
Plus work done from point A to B by non-conservative forces equals to kinetic energy at B plus potential energy at B. That's all. That's the whole equation you need to know. All right. So now we're gonna have to eliminate some.
We could
eliminate. At A, see, you see, this is the kinetic energy at A. Is there any kinetic energy at A?
No.
Well, what does it say? A student throws a 10-kilogram ball up into the air with an initial velocity of 60 meters per second. Is it moving at point A?
No, it's not moving. It's moving in between.
Well, in this case, since here V initial at A is 60 meters per second. So at A,
it is initial. Velocity. Oh yeah.
So it is moving.
A is VI, yes. And then the B is V final.
This one? V final will be here.
Okay.
So there is kinetic energy, so we can't eliminate that. Next, is there potential energy at A? It's at its 0 PE level.
Oh, 0 PE. So does it? It has 0.
Yeah, 0. It says right there 0.
Oh yeah, plus 0. So we could just put plus 0.
It's at its lowest point. So we could zero that out. See, we're gonna eliminate.
Oh, okay.
Yeah. Well, is there any work done by non-conservative forces? So is there any applied force? Is there any tension force?
There's
Is there any
applied force?
Does that tell us that it told us? Well, it didn't tell us.
He throws it. I mean, that's an applied force. Throwing.
Well, throwing. Well, it didn't say that he exerted a force onto it.
Okay.
Yeah.
So
here.
There's no.
So here, there would be no work done. Is there any work done from A to B?
Yes.
Meaning is there? Let's say, so work done by an applied force. So an applied force. An applied force. And things like that. An applied force, or is there any tension force? Well, there's no applied force. It didn't say that he applied any force. And remember non-conservative forces, so we go all the way backward. Okay, so conservative forces. It's not asking for that. It's asking work done by non-conservative forces.
So which one doesn't have? Yeah.
So non-conservative forces, they don't meet the criteria above, meaning an F applied, a push, or a pull.
They don't lose energy.
Yeah, exactly. Is there energy being lost here? That's what it means.
No.
Is there? Nope. There's no energy being lost. So you could ask, is energy being lost?
For NC, right?
Yeah, due to a non-conservative force. Due to a non-conservative force. The answer is no. So you could just zero that out as well. Is there any cause for it to lose any potential? If there was friction force, then you would have a work being done. But right now, there's no work being done. Yep. Now let's look at B. Now we looked at A here. So now B. Is there any kinetic energy at B? It's at its highest point now.
No, it's no. Zero.
Nope, it's zero. But there is potential energy, right? It's at a height.
Yes.
It's at a height. So
But we don't
all we're
know.
left with is
We don't know what height it is.
Yep, that's what we're solving for. How high
Oh, we can
would the
plug
ball
in
go?
PE B equals MGH.
Yeah, and MGH. But remember, it's not just any MGH. It's the H final.
Oh, MGH final. Yes, yes, yes.
Yeah, so the A would be the initial. B is final. So A stands
equals
for the
each
initial.
other.
What happened?
They're equal to each other.
Yeah, they're equal to each other in this case. So here, so you say therefore
1/2
kinetic energy.
1/2 mass or something.
So kinetic energy, remember, it's 1/2
mass
mv squared.
Velocity squared.
Right here, 1/2 mv squared.
Okay.
Yeah.
Damn, this is fun.
Okay, so 1/2 mv squared, and this will be initial because remember it's A, so that's the beginning, which equals to potential energy, or not potential.
MGH.
MGH.
Yes.
H. This will be the final. We're looking for that.
Yes. But then.
So now here's where you. Yep.
Okay, there's no angle. There's no angle. Never mind.
No, there's no angle, so we don't got to worry about that.
Okay, good.
So the mass, we know it's 10 kilograms. V initial is 60 kilograms. 60 meters per second. What am I saying? 60 meters per second. 60 meters per second. Which equals to MGH.
You forgot to put the squared.
Oh, yeah. Squared. There we go. So 10 kilograms. G is just 9.8, right?
Yes.
Meters per second squared. And the H, you see, that's what we're solving for.
Oh, there's no negative 9.8? No?
No, there's not negative 9.8. Remember, here we're dealing with the magnitude of G. Yeah. So half of 10, that's 5. Then 5 times the square root of 60. Not squared. 60 squared. We got 18,000. Well, we see we got kilograms times meters per second squared times second squared. That gives us joules.
Yeah. It's a KGS, right?
10. Yeah, you see you see how it's squared? It's going to be meters squared per second squared.
Yeah.
And then kilograms times meters squared over second squared is joules.
Oh, snap. I think you erased it. Oh, you just wrote joules.
Oh, right here.
Oh, yes.
Kilograms.
Yes.
Meters second squared.
I see.
Yeah. And this will be 10 times 9.8, which just be 98, I think. Yeah, 98. So this will be 98. Again, kilograms. But this one here is kilograms. GH, I'm missing something. So kilograms. Well, this will be kilograms. Meters. Second squared. In terms of height final. That's weird. How come I do not have? Oh yeah. Oh no. Because we're gonna get meters, right? So yes, it's gonna cancel out.
Yes.
So we're gonna divide 90, and this one here we have H final. So this will be 98 kilograms meters second squared. Divide that by 98 kilograms meters second squared. So we're gonna have 18,000 divided by 98. We're going to get 183.67. Here, joules, remember, is the same thing as kilograms. Meters squared over second squared.
Oh, you have to go back and forth.
Yeah. That's just to show you that this was joules.
Yeah.
But I'm gonna show you how at the end I'm gonna get meters.
Okay.
The values are just gonna cancel out. Kilograms, meters, second squared. So here the second squareds are just gonna cancel out.
Yes, yes.
Kilograms also cancels out. Meters as well.
One
We'll be
cancels
left with
out,
the
and then
one.
you have 1 meter left.
And then we the H final equals to 183.67
Meters.
meters. And that's how you get your answer.
Oh, so what did we just find? We found the height, final height.
Yeah, we found the height. It said that a student throws a 10-kilogram ball up into the air.
We never did that, right?
With
We never did that before, right? Finding the height before?
Yeah, but with kinematics, though.
Oh, we did it with kinematics?
Yeah. I mean, you could probably still do this with kinematics, but this is with energy. It's another way to do it.
Okay.
So, like, if let's see, we got a mass, but we only got V initial.
We only have 2 stuff, so we couldn't. We wouldn't
we really can't. But if we had enough information,
we would.
like an acceleration or a displacement, well, we have height now, but it doesn't. It will just go back and forth. But yeah, if you had enough, you could do kinematics, but with energy, you could just use this instead. Yeah, because it really is a motion. It's a motion problem, but
you could just use it by using that equation.
Yeah. You see how it's more easier than the kinematics.
Yeah, you had like 4 variables. Yeah.
You have to choose. You have to choose which equation to use.
Exactly. Yeah.
Here is the problem. The only problem here is you gotta know everything above. You gotta know what kinetic energy is, what everything else is above. You need the concept.
Does it get easier than this? Future?
Does it get easy? A little bit. It does. Yeah, some points. I think so. I think so. I think so. The collisions is an easy one.
Yeah. Stephen Hawking, he was trying to find one equation that explains everything.
Yeah. Now I say energy is harder than the collisions. But
wait, energy is harder than collisions?
Is challenging because of the concepts.
So what's the hardest right now? One dimensional vectors. That's the hardest for me.
Hardest for me, the hardest probably would be. I think energy might be the hardest for me.
It is.
To me, yeah. I mean, I could do it. I'm just saying, like in terms of measuring, what's harder.
Yeah.
To me, I think energy is the more.
Yeah, because you got to convert it. Is it because you got to convert it, and if you mess up your conversions, you're screwed?
Yeah, but the only reason why to me it's challenging is only because
so much information.
Of the concepts.
Yeah.
Yeah. But I already got the concepts down, but before when I started, it was.
Yeah, so after energy, I keep asking the same question. After energy, what we got left?
Yeah. After energy,
we got collisions, you said?
We got power.
You got power. That's energy, you said, right? Something like energy?
Yeah, that's part of energy. That's where you got the watts.
Snap. No.
Now, that's only one topic, though. There's only one page.
Oh, okay. That's good.
Power just equals work over time.
Oh, yeah, I didn't know that.
And then you got Newton's law of universal gravitation.
Oh, okay. How long is that? How many pages?
There's only like 1.5.
No, okay. 2. Then after that?
Then after that's momentum, which is a longer.
Oh, seriously?
More concepts. Yeah, more concepts like this.
Oh my god.
But it's easier.
It's killing me.
But it's easier to understand. It's easier to understand though.
Oh, no, okay.
And after momentum, you got relative velocity.
Do you know if Michael Van Wezen, does he have like any videos on momentum or stuff like that?
Yeah, he does.
He does? Okay.
Yeah. So.
Okay. I'm gonna check it out later.
Yeah. All right. So now taking the second example.
Yeah.
And you could say the harder one. Yeah, the harder one.
All right.
So 2. This one has an
Brace yourselves.
This one has yeah, so a 20 kilogram object is pushed.
This is applied.
Yeah, it's pushed along a horizontal. Now guess what? You have a mu, meaning you have friction.
That game was so fire.
Hmm.
You watched it?
No, there wasn't.
So fire. Scholars Grind, right?
Damn, they only give like 2 stuff, and you just gotta use it based on like you gotta cancel them out with zeros, right?
Yeah. Yeah, that's the thing. You gotta know the concept
So
of
how about
the hardest
momentum?
part.
Is more zeros?
More zeros, yeah. You have to cancel some stuff out.
It's more easy than this though.
But
Momentum.
you still use energy and momentum.
Oh, you still use the same
it.
formula?
So not the same formula.
Oh, okay.
Similar. But
Okay.
you still use kinetic energy and potential energy. Still
Oh,
do.
you do. Okay, it accumulates like
Yeah.
you said.
Yeah, again, yeah, like I said, accumulate. So you gotta know.
Gotta be ready.
Fast. Yep. So what is the velocity of the block after it travels? 100 meters. So, what do you always do? You draw it out. You draw it out.
Draw the free body diagram, whatever you call it.
Nothing but draw it out.
So a 20 kilogram object gets pushed away in a horizontal line. There could be a square, right?
Here?
Square?
Yeah, it could be a square. It could be a rectangle, a circle.
Mm-hmm.
So here it says a 20 kilogram object. So this will be 20 kg.
Mm-hmm.
It's pushed along horizontal.
That's applied.
Yep.
What is that MK? Well, kinetic?
It has mu k. We have friction.
Oh, we have friction on the bottom of the floor.
Yeah, so there's some friction.
That's like MK. That's like, what do you call that? That's if it's
mu
0.2. Like if it's more towards the 0, that means it's frictionless, right?
Yeah.
But it has friction now.
Yeah, we have friction. We're gonna have to use Newton's laws now. It's gonna be a combination of Newton's laws, energy.
Oh snap! Okay,
and trick.
Oh yes.
Some simple trick.
Oh okay. So this one has the weight or gravity force.
Yeah. But we're not done yet. We're not done labeling yet.
Okay.
So it says a 20 kilogram object is pushed along a horizontal with a horizontal force
of 80 newtons.
Of 80 newtons at an angle.
Oh, so it's going up. It's going up. Yeah, like that.
Yeah, like that. So this is the force applied.
Yeah. So we have to deal with the angles. 30 cosine, the x components.
This is the one that you'll probably see on the test.
Oh, okay. You have to know 2 components or 1 component only?
Well, it depends for the work. Remember, the work you use the same. You use the component and that goes in the same direction as the displacement. So this right here is F applied Y.
F applied X.
This is 30 degrees. And this is F applied X. Well, you have friction. They told you, see?
Yeah.
You have kinetic friction. So what way am I going to draw the kinetic friction?
Kinetic friction. Kinetic friction is.
Come on.
Wait, what did you say?
What way would I draw the force of kinetic friction? Because they say mu sub k. So we have friction. So
oh yes.
Right now
it will go. It will go the other way.
Opposite, right?
Yeah.
Opposite the direction.
Yeah.
This right here is the force of kinetic friction.
Yeah, you know what I thought? This is what I thought. I thought it was like the other way, angular.
Oh, this?
No.
Oh, you thought it was at an angle?
No. I thought the opposite angular. Like, you know how that's 30 degrees? I thought the other one was like other 30 degrees. To the left.
Oh, no. Now, remember, a force of friction is always opposite the direction it's moving?
Yeah.
Yeah. Okay, so now this is, remember, if we go back to the method to solve problems. Draw the problem out. Label the 0 PE reference level.
Yeah, don't forget that.
Level point A at the starting point and B at the ending point.
Oh. So 0 PE reference is on the floor.
Well, yeah, this is the 0 PE level, so it looks like we have no potential energy at all.
Mm-hmm. I
If
mean,
the object was like up in there, then yeah.
mm-hmm.
So that's A. We just drew A. 20 kilograms. This is at B.
Oh, okay.
And they told us it has a displacement. It travels 100 meters.
Hmm.
So all the way over there, displacement equals 100.
So it was thrown or something?
No, it was just pushed along.
It was pushed along, but what is the degrees? What does that do?
This one.
Yeah, it was pushed up or something?
So it looks like somebody's pulling it, probably.
Oh, okay. Somebody's pulling it. Okay.
Yeah, you see, yeah, so like you and you're pulling just some at an angle.
Hmm. You see.
Yep. So like always, we write out the famous famous loco
Mm-hmm.
equation, kinetic energy at A.
A K E B. Oh,
That's
that
brilliant.
green. That green is a
Yeah.
bad color. It's like so.
Oh, you can't see it?
Yeah, barely.
Okay.
You have dark green or something.
Yeah, wait, hold on. I'll change the color. I'm just write it out.
All right.
So this is the work from A to B, non-conservative, equals to the kinetic energy at B, plus the potential energy at B. Now I'll change the color.
Mm-hmm.
Style.
Yeah, that's better. Oh, you have a bunch of colors. Go swipe.
Yeah,
I didn't know that.
yeah, you could choose, yeah. Okay, so now it's time to apply concepts. Here at A, is there kinetic energy at A?
Kinetic energy. Yes, there's no potential energy, but there's kinetic energy.
Yep, because it's moving.
So potential energy we could cross out.
Yep, we could zero this out. Is there any non-conservative forces? Any work being done by non-conservative
Yes, there's
forces?
applied.
Yep, and applied with and the friction, remember?
Oh, your friction also. Yes.
So we leave that alone.
What are non-conservative forces? It will be applied forces, friction forces. What else?
And just applied forces and friction forces.
That's it.
Yeah.
Oh, okay.
Yeah, but remember, kinetic energy causes a loss of energy.
Loss of energy, the heat or something.
So remember what we asked. Is energy being lost due to a non-conservative force here?
Okay.
You see nothing. There's no.
It is being
no
lost because of friction. Friction energy.
Yeah, but here there's energy being lost due to the friction.
Yeah.
So now, is there any kinetic energy at B?
Any kinetic energy at B? Yes.
At B? Yes. How about, is there any potential energy at B?
No, 0 PE.
Yeah. 0 PE.
So now, what we got?
Mm-hmm.
So that NC over there, would we just make it F net?
Which one?
NC. Yeah. None. Yeah.
Oh, this one?
F net.
Well, this one, remember work?
Oh, that's integration,
equals.
No? Oh, that's not integration.
No, that's when it's not constant.
Oh, okay.
Yeah. So constant is by a force.
Mm-hmm.
Some force by some displacement.
And then cosine of the angle, 30 degrees.
Yeah, but, yep. Cosine.
I gotta practice one of these.
That's the one. Yeah. Well.
This is fun once you know what to do.
Yeah. Once you know what to do, it's easier to do.
You gonna make your own theories, bro?
Nah.
Why not?
Nah.
Make your own math like Isaac Newton.
Nah.
And you could die a virgin like him too. He died a virgin.
He died a virgin.
For real.
What?
He died a virgin. You don't know that?
Damn. Too bad. Too bad.
That's what happens when you invent calculus, right? No, stop.
Yeah. So, yeah. Well, actually, is there kinetic energy at A?
Kinetic energy at A. I feel like there is. Where'd you go, bro? What the heck is this?
All right, I'm back. I'm back.
You back?
I'm back. Yeah. Okay. Where the 20 kilogram object is pushed along a horizontal surface. Okay. With the horizontal force of 80 newtons.
Hmm.
At an angle above 30 degrees horizontal, what is the velocity of the block after it travels? This is the key word right here.
After.
Yeah, what is the velocity of the block after it travels 100
So after
meters?
it gets there.
Yeah, after. So right now it's still then.
Hmm.
Right here, the object is still.
So there's no kinetic energy
Yeah, there's no kinetic energy.
because it's still.
Yeah, it's still because it still hasn't moved. It's gonna move after it travels 100
Only potential
meters.
energy is when it's still.
Yeah. Well, it's not even potential energy because remember it's at the 0 PE level.
Yeah, there's no potential energy in this case.
Yeah. And here we got B. Well, it is moving. Remember, because it says after it travels.
Mm-hmm.
Yeah. So right there we assume it's traveling there. And then the work from A to B.
Mm-hmm.
Well, there's an F applied in the X direction. There's force of friction.
Mm-hmm.
We have to find the net force. This has to be F net to find that.
Oh, okay.
Yeah.
So, F applied is F net. Oh, that is F net. What am I saying?
Well, let's bring this mass down here. Let's do the free body diagram.
So, we will have
since
to.
it's still, what else does it have? It has V initial equals 0, right?
Where?
Here, since it's not moving.
Oh, it is 0. Yeah.
So it has V initial equals 0.
And then V final, we don't know yet.
Yeah, that's what we're looking for.
So, F net, it will be to find work of non-conservative. We would have to do magnitude. What? 80 newtons.
Well, remember, what are we going to have to do? We're going to break down these components, right?
Oh, we do. Yes.
Yeah.
So it will be F applied of Y over H. Which is.
Well, here the F applied Y, well, that'll be sine. Sine is opposite over hypotenuse, so it'll just be 80 sine 30, and then F applied.
What? X. 80 sine 30? Oh, 80 is.
Yeah, because remember, it's at a 30 degree.
Mm-hmm.
And then this is the magnitude.
Oh, yeah. Magnitude is 80. Oh, yes. Oh, that is the magnitude. 80 is the magnitude.
Yeah. Yeah, remember cosine opposite
Yeah, over
is a y.
hypotenuse.
Oh, yep, it'll be opposite over hypotenuse. So it'll be f applied over 80, and we'll multiply 80 on both sides.
Or F applied over 80. Oh, we went ahead. Okay, I thought like we're doing it
Yeah,
slowly.
nah,
Oh,
nah.
all right, we got it. I got it.
Yes, yeah. So now, well, that's it. That's the only angle that we had to break down. Well, here on the floor, but remember kinetic friction. How do we calculate kinetic friction again?
Kinetic friction.
Yeah,
So we would do it by mu times the g or something. Forget.
mu times
times
the
the
normal force.
normal force.
So here,
yes, we forgot to label
we're
the
gonna have
normal
to draw.
force. Yeah,
So now we're gonna have to label us up
normal
normal
force, and then we
What
have
else
the
do
weight. We have the weight.
We have the weight, which equals mg.
Yes, yes.
Yep. And now we're only gonna solve now for the normal for the y direction. Why? Because remember norm f.
So
Kinetic friction
0.2
equals-
times normal force. We don't have normal force yet.
Nope. That's why we're gonna calculate it for. So we're gonna start with the y-axis. And remember, it's not right here. It's not moving at all, right? So what law is gonna apply here to both directions? Which Newton's law?
It's just first law.
Yeah, the first law, because remember it's not moving. And what does the first law says?
If F net equals 0.
Yeah, F net equals 0.
Damn, I came a long way.
Positive.
I don't feel dumb anymore.
No, man. So positive up is y, right?
Yeah.
So how do we write that?
We could write normal force minus mg.
What else? Look at the F applied y. Remember the F applied y?
Oh yes. F applied
so
to
that has the direction
yeah,
up,
we would
so,
plus F applied to y.
Yeah, so it'll be plus F applied y. Minus now the
minus mg or w. Correct. Yeah.
Yeah. Which again equals to the normal force. I'm gonna move that to the
right side.
This equals 0, and then I'm gonna move it.
Yes, and then you can move it to the right side.
So now I'm just gonna move all of this to the right. So normal force equals to the weight
W minus F applied to y.
F applied y. You see what I did here?
Yes.
This became a positive, so I put it in front. This became a negative, so I put it in the back.
So we could do 20 times 9.8.
Yeah. So weight is the mass is 20. Yep. Times 9.8. Minus F applied
y is basically 80 sine of 30 degrees.
Well, we didn't calculate, so let's calculate that. Let's calculate that. So it'll be 80 sine 30 equals to 40 exactly. And 80 30 cos 8 cos 30 is 69.28. 69.28 newtons. Newtons. Okay, so this will be minus 40. And 20 times 9. Blush.
Thank you.
Yeah. 196 minus 40. The normal force minus 40.
116.
156 newtons. We found the normal force, but that's not what
plug
they're
it
asking
in.
us.
Yeah, you can plug it in.
Yep. Now we're gonna plug this number in.
With the 0.2.
To the force of kinetic friction.
The mu of K is 0.2.
Yep, that one. So now force. So therefore, force of kinetic friction
equals 0.2 times 156 newtons.
Yep. Force of kinetic friction equals to 0.2, right? Yeah. Oh no, it's 0.2.
I wish I was a human calculator.
39.2.
Okay. Now we gotta plug it in more, no?
Now you see we got the kinetic friction. We could plug that in by the displacement cos theta.
Yeah. I see it.
Now, So now we could do that, and we could also do it for the F applied. But which?
Nope.
Well, but which would I use F applied Y or F applied X to find the work?
To find the work, you would use F applied X.
Yes, remember they have to be in the same direction
Yeah.
as the displacement. Remember the displacement
It's
is
going
going
from
that way,
yeah.
and this is also going that way. So we use the
Yeah.
ones parallel to each other.
Yeah. 100 meters to the right. Yeah.
Yeah. So now we could. I'm gonna bring this equation now.
Yeah. Bring it down.
Copy. So now I'm gonna bring this down. Good. Okay, so the work of non-conservative forces would be force of friction, right? Force of kinetic friction times the displacement.
Wait, is that F net over there?
This one?
No, W after W. Yeah. What is that?
Yeah, that's F net.
Okay.
So this is I'm just gonna do it separate. So it's gonna be force of kinetic friction times the displacement cos theta. But what?
30 degrees.
But what's the theta?
30 degrees.
What's the what's the angle between F applied X?
Oh, it's 180.
And kinetic friction. Yep, is 180. Or I should say, what's the what the thing that you should ask is what's the angle between the displacement and the kinetic friction?
Oh, displacement and the kinetic friction.
Yeah,
which
so
is
here
180.
180. This will be plus now. What other do we have? We have the F applied X, right? So this will be F applied X times the same thing, displacement. Now cos what?
Cosine of 30.
What's the angle between what's the angle between the displacement and F applied X?
Oh, that's only 30 degrees.
Well, they're at 0 degrees, remember? They're in the same direction.
They are in the same direction.
So
wait, what was your question?
Oh. What would be cos? What would be cos? The F applied X times the displacement. What's the angle between the displacement and F applied X?
Oh, that is 0 degrees. Yeah.
Yeah, you see how X and the displacement are in the same direction.
Oh, yes.
You see, we don't care about the Y because that'll just give us it'll zero out.
Oh, okay.
Yeah.
So first one was displacement. The distance between displacement. I mean, the angle between displacement and the kinetic friction or something?
Wait, the angle, this angle?
No, the first one. First angle.
This one?
Yeah.
Oh, yeah, this was the angle between the displacement and kinetic friction. So the displacement is going that way. And so we got, that way, and then that way.
Oh, okay, so 180.
This angle.
180.
Yeah, that's why.
Yeah, how would you know that, though? We're solving for that, though, right? That's why?
Yeah, well, it's always really the angle between the displacement and whatever force is non-conservative. In this case, the kinetic friction and the applied. Yeah. So now this is equal to kinetic energy at B. So remember that equals to 1/2 mv squared.
Yes.
But this is the final. Yes. That's final because it's at B. So now we know the magnitude of this one, right? Kinetic friction, we just found it.
Yeah, 39.2.
So that'll be 39.2. The displacement, we know it. 100.
Yes.
They gave it to us.
Yes.
So now it's more plug and play now. And cos of 180 is -1. Plus,
so that would make it minus. That would be a negative force. I mean, negative work.
Yeah, it is negative work. Yeah. And then F applied X. Well, we know what that is. That's 80, not 80 newtons. That's 69.28. Because we found that 69.28. The displacement we know is 100. And this is times 1, right?
Yes.
And this equals to 1/2 m. Well, not m, but now here it weighs 20, I believe. Yeah, 20 kilograms times V final squared. So now if I plug all of this into the calculator, so 39.2 times 100, that's a minus 3,920 plus 69.28 times 100 is 6,928 equal to 10 V squared, V final squared.
Mm-hmm.
And then we take the difference between that. So minus 3920 gives me 3,008.
Wait, minus 39?
I did 6,928 minus
390, honey?
Yeah.
Okay.
Yeah. 390.
So we divide now?
Yeah. But hold on, let me check. Make sure everything is correct.
Okay.
So 0.2.
Yo, you think he's gonna give the hardest questions?
Probably, but the good thing about him is that he won't. He gives you everything. He gives you everything you need.
Oh, okay.
Oh, I did a mistake. This one is not 39.2. It's 31.2.
Oh wait, it was?
Yeah.
Oh.
Not 39. So this will be 1. This will be 1. 3120. So let me do 31.2. If you don't mess up here, you could mess up here.
Wait, what was it? You did. You did.
Yeah,
no, down there. No, down there.
Yeah.
No, right there.
Where?
No, 33. Wait, 3.120.
Yeah, it's 31.2.
Oh yeah.
You got the same number?
Yeah, but when you multiply 31.2 times 100, what did you get?
Negative 3,120.
Oh, that's a 3,000? Oh, I thought you said 3 point. That's what I thought.
Nah.
Okay, good. I thought it was a point. That's why I was concerned.
Yeah. 69.28. This one is not negative. This is 3,808.
Okay.
Divide 10 on both
by
sides.
10, yeah.
So 3,808. Divide that by 10. I get 380.8 equals to V final squared. But
now we
we're
got
taking
square
the square
root,
right?
Yeah. It will be plus minus.
Plus and minus.
Yeah.
But we only care about the positive positive velocity.
Because it's going to the right.
Square root.
Yeah.
Yep. Therefore, V final equals to 19.51.
Okay.
And that's what you had to do to find.
Now that's like 2 pages of work.
Yeah. So you see how much work. All of this is how much work we had to do.
Yeah. Holy cow.
Yeah, you see, it's a mix. This one was a mix. It had angles.
Yeah, everything.
Newton's laws. Yeah. Yeah, normal force. You see how you still got to know your forces.
Yeah. It comes back. Newton's to you. Comes back to screw you if you don't know it.
Yeah, man. And now the addition of energy.
Why did Isaac Newton have to do us like this, man?
Oh man. Yeah.
Right.
That's how you would.
So this is everything about energy?
Yep, this is everything about energy and then power.
Okay.
Power is short. Power is mass short.
Should I end this one?
Yeah.
Okay.
Yeah, just end.